that travels as signal. It could be digital or it could be analog. And then we reviewed the reasons why analog is not good and why digital is good. And then we also discussed that either it's analog or digital, delay is an important factor, and delay is directly proportional to the number of bits in my message. It is indirectly proportional to the bandwidth through an equation. The other components of the equation, for example, the distance and speed of light, so we said we cannot do anything with them. Then when we became convinced to, so that's all happening in signal in quadrant 1. So when we were convinced by digital, then we thought we should convert analog to digital. Once we decided this, then our eyes set at digitization. When our eyes were set at digitization, we said in digitization, the first thing we need to do is we need to do sampling. Then we say, okay, we need to do sampling. How do we sample? Then we said we should sample 2WS, and that was told by Nyquist. Then say we have sample, then we need to quantize. And quantization impacts heavily. Number one, you had known error. You're knowing it's error, but you do quantization error because you have to round off to those digital values. Then you have to see, in reference to that, how many levels. And then you have to see, in relations to how many levels, how many bits. And that would impact your R. And that would impact the effect of noise on your signal. I mean, if you go too low. So then related to signals, we say if we have analog signal, we can do sample, we can quantize, and then we will be sending whatever our samples are. They would be in zeros and ones. So we will send them. So we started with sort of a waveform, and we ended up having zeros and ones, and they would go from sender to receiver. So we said if we do these things, so that's how we deal with signal. Then in the same quadrant, we can also place, okay, what is the nature of signals usually? You can have digital signal, or you may have waveforms. Waveforms could be pure, or they could be composite. Shapes of composites, I mean, I can have a square waveform, Sawtooth waveform, for example, or triangle. So then we said a waveform could be a pure or composite. So still we are on signal side. We are talking about the signal, pure or composite. So if it's composite, then we said it is made up of various harmonics. We said harmonics could be odd and even. And then we had all that discussion that if I'm going to make an increasing waveform, I'll be needing odd harmonics, and then I'll be needing even harmonics. Where is the power? Where is not the power? So we said majority of the waveforms in the real world, they are composite waveforms. A little better, okay? Then this is how, so that was how the waveforms are made. Then we said how we analyze them. Another thing is how we analyze them, right? Then we said a waveform can have, depending on may or may not have a DC component. It will have a cosine component and it will have a sine component. And then we said once we have DC, may or may not, how we know that? Through visual inspection. And cosine and sine, they're there. And when we have cosine and sine, then we said they would be having coefficients. And we can find those coefficients, an and bn, for example, and they are a series. So sine and cosine here, they are a series, right? So then an is representing the variable n. It would be a naught, a1, a2, sort of all those. A naught is for DC, but a1, a2, a3 all. So I will be having. So if I can find these coefficients, an's, bn's, I will be needing something like Fourier series. So through Fourier series, I gave you formula. I can find ANs and BNs. And Fourier series, we said, is that's where the Fourier series in the context of signal was into the picture. And then we said, yes, but Fourier series is for periodic functions. And for non-periodic, we said you need to have Fourier transform. So kind of that's what we talked about in terms of signal. Then from there, we entered into another quadrant number 2,